In thermodynamics, we classify variables as variables that describe the state of the system, state variables, and variables that describe transfer of energy in and out of the system as transfer variables. For example, for a gas in a cylinder, we can use pressure of the gas, P, volume of the gas, V, temperature of the gas, T, internal energy of the gas, E internal, to describe the state of the system. So I'm going to call these variables state variables. And actually they are related. Remember, in ideal gas law, we have PV is equal to nRT or capital NKBT. That's called equation of state. And internal energy is basically describing the total energy of the system due to the motion of its molecules as viewed from the center of mass reference frame. Now we also have these variables that describe the transfer of energy. So heat and work, the transfer of mechanical energy by work, the transfer of energy due to a temperature difference, heat, we call these transfer variables. And now I want to think about an experiment where I have a gas in a cylinder that's trapped in a cylinder. So this is normally under equilibrium. So at the beginning I have an initial volume V initial, there's an initial pressure P initial, and the outside pressure must be equal to the pressure of the gas so that the system stays at equilibrium. The walls of this cylinder are thermally insulating. So there is no heat exchange with the environment. So all I can do is push this piston by a certain amount. Now when I change this pressure, when I increase the pressure just by a little amount, so P initial plus a delta P, what I find is that the system will reach a new equilibrium condition where the pressure of the gas will be increased to P initial plus delta P, the new pressure of the gas, and then it will reach a final volume which is V initial minus delta V, so there will be a small decrease in the volume. So this is going to be a compression. Okay, so the way I'm doing this, increasing the pressure on the gas, I'm adding, let's say, 1 sand particle at a time. So I have these sand particles that are dropping on this piston and very slowly increasing the pressure on the piston, and therefore every single time I drop a sand particle, since I wait long enough, I reach the new equilibrium condition. So this is at equilibrium at all times. And I will repeat this process until the P initial becomes P final and V initial becomes V final, so that the volume and the pressure of the gas will be changed. All right. So while compressing this gas, a gas in a cylinder, the system stays at equilibrium at all times. And how do I do this? I do this increase in the pressure so slowly that I disturb the system just a little bit, and equilibrium is re-established at every single step of the compression process. This is called quasi-static compression. Quasi-static compression. Okay, the work done by the force, the total force that we're applying here on the piston is going to be equal to the force dot product with the displacement it causes. So let's call this axis y-axis, and I see that the force that I'm applying is in minus j hat direction, and the displacement it causes is dy in j hat direction. So it's going to be equal to minus f dy, but since the change on the y-axis, the displacement on the y-axis dy is negative, I will find that the work done by this force is positive. All right. So what is this force that I'm applying? The force that I'm applying is the pressure times the area. So by definition, pressure P is force divided by the perpendicular area. So what is this perpendicular area? The area, cross-sectional area of this piston. So that's area A. And as I compress it, what happens? This piston is moving down, and I have basically changed the volume by a certain amount. By how much? So by this amount. This change in volume dV is going to be equal to the cross-sectional area of the piston times dy. So the force that I'm applying is going to be equal to pressure times area. So I have minus pressure times area times dy is equal to the work done. And area times dy is the change in the volume. So it's minus pressure times dv. And once again, dv, the volume is decreasing, dv is negative. Work done by this force is positive. So I find that in the quasi-static compression process, the work done in every step is equal to minus pdv, so that the total work done in going from an initial volume to a final volume is minus integral p dv. So that's the quasi-static work done in every step, and this is the total work done, which is found by integrating the work done at each step, going from an initial volume to a final volume. So I find that the total work done, since V final is going to be less than V initial, delta V is negative, work done on the system is positive. There is work done on the system. What is the work done by the gas on the environment? That is negative. So this work is basically work done on the gas. So it's the external environment that is doing the work, so that is exerting extra force in order to cause a change in the volume. Now, if I look at a pressure volume graph, remember that for an ideal gas, for example, PV is equal to nRT. Now, if your gas is in this insulated cylinder, there is no heat exchange with the environment, temperature is constant, so we have no heat exchange, so there is no Q entering the system. However, I'm doing work on the system, so the temperature may change. However, if I connect it to a heat reservoir also at the bottom, so that fixes the temperature, then I would have what is called an isothermal process. So that's the situation here. We have isothermal compression, isothermal compression or expansion. And what does that mean? The system is basically isolated from its environment, so these walls are thermally insulating. So there is no heat exchange with the environment. However, when you look at this boundary is different. This is basically connected to a heat reservoir, and heat can be exchanged with this reservoir. Okay, and what is an energy reservoir? So let's define energy reservoir. Energy reservoir or heat reservoir. This is going to be a source of energy, which has with a very large heat capacity. So remember, heat capacity was defined by this equation. Q is equal to C times delta T. It's the amount of energy you have to provide to the system to change its temperature by 1 degree Celsius. If C is very large, then a finite amount of heat transfer, heat does not change its temperature, because the change in temperature is Q divided by C. C is way too high, and therefore delta T will be very small, so there is almost no change in temperature. So while this system is exchanging energy in the form of heat with this energy reservoir, its temperature doesn't change. So if the system stays at equilibrium at all times, the temperature of the gas will stay at this initial temperature, because the temperature of the gas is fixed by the energy reservoir. Okay, so that's because we have at the bottom a thermal contact. There is a thermal contact with a heat reservoir which fixes its temperature. Now, in this situation where I have no heat exchange with the surroundings, if I make a thermal contact with the bottom also, the temperature will be fixed as well. So we can talk about this more later on. So let's assume that I have isothermal process. Isothermal process implies the P times V is a constant. So if you plot pressure as a function of volume, you will see that you will get so-called isotherms here. So there is a corresponding temperature T, so that PV is equal to nRT, or in other words, we can say that pressure as a function of volume is nRT divided by V, where T is fixed if it's an isothermal process. Now, if I try to calculate the area under this curve, and if I do this in going from V initial to V final, P initial to P final, so basically I follow this path, the area that I will calculate will be integral from V initial to V final, P dV. However, the work done on the gas is going to be equal to minus the integral from V initial to V final P dV. So therefore, the area and the work have a relationship, they are related. The work done on the gas is minus the area under PV curve. Alright, so I find that the work that I will do will be positive if it's going to be a compression process. So the work done on the gas will be positive if it's a counterclockwise motion on the PV diagram. So that means I'm going from here to here. The work done on the gas will be negative if it's a clockwise motion. That means I'm going from an initial volume to final volume in this direction. How do we see that? From this curve here, the area from going from V initial to V final, P initial to P final, is integral P dV. Since V final is less than V initial, delta V is negative, so pressure multiplied by a negative delta V with a minus sign gives me a positive work done on the gas. Now, if you look at three other processes that takes me also from V initial to V final, the process that I will look at here is one where I fix the pressure first. That's called, this part of the process is called isobaric. And then I fix the volume, and this part of the process is called isovolumetric. Constant pressure, this is constant volume process. So what is the work done going from P initial, V initial to P final, V final using this process? Well, since the isovolumetric process does not have any volume change, it's going to have no contribution. The work done will be equal to minus P initial V final minus V initial. The area under this curve, if I calculate the area here in this direction, it's going to be equal to P initial times V final minus V initial. However, the work done is going to be minus P initial V final minus V initial. So that's the work done in this process. Let's call this process 1. That's the work done in the first process. In the second process, I start with an isovolumetric step. So I keep the pressure constant. This is isovolumetric. And then I keep the pressure constant, and that is isobaric. Now the work done in the second process will be equal to minus P final, V final minus V initial, and again V final is less than V initial, so this is going to be a positive work done. So any other process that takes me from P initial, V initial to P final, V final will have an area. This is area of the first process, area of the second process, area of any process, let's call X. This area of this process will be in between A1 and A2, and the work done in going from P initial, V initial to P final, V final with process X will have a value that is in between W1 and W2. So any process will have that have an intermediate area will have a work that is in between these two extremes. So therefore, in going from P initial, V initial to P final, V final, the minimum amount of work I can do is this one, minus P initial, V final minus V initial. The maximum amount of work I can do on the system is minus P final, V final minus V initial. All right, and so we talked about the isothermal process as well here. What I would like to point out is that regarding the heat capacity of the objects, if you're trying to fix the temperature of a system, we use an energy reservoir which has a very large heat capacity. If we are trying to measure the temperature of a system, basically we want the opposite. We need very small heat exchange with the system, and that's going to change the temperature of the probe that we're using. So for a thermometer, on the other hand, if we're trying to measure the system, we want to have the amount of heat that we need to change the temperature to be as small as possible. C is equal to Q over delta T, and I want a very low heat capacity, so that the change in temperature delta T will require a very small heat. So that means a thermometer will not disturb the system whose temperature we're trying to measure. It will have a negligible effect on the temperature of the system. There will be a very small amount of heat exchange required. So that those are two extremes. So energy reservoir has a very large heat capacity, that's for the energy reservoir, and for a thermometer I need a very low heat capacity. So C should be as low as possible. Now there's one more process I would like to look at, and this will be a model process for us for some of the rest of the discussion that we will go through. Now I have a gas that is initially at temperature T initial and contained within a vessel, a cylinder, and it is underneath a thin membrane with vacuum above it. Okay, so the pressure at this region, the top portion pressure is 0, and I have this thin membrane, so that is basically fixing the initial pressure, initial volume, and initial temperature of this gas. Now the membrane is broken and the gas expands freely into the evacuated region. Okay, so basically I eliminate the membrane is broken. What will happen is that the gas will expand to fill the rest of the volume here. So there will be a final pressure P final and a final volume V final and a final temperature T final. Now what I would like to note is that these walls are insulating walls. If you have insulating walls, there is a thermal insulation, and that implies that you don't allow heat exchange with the environment, and we call that an adiabatic process. So adiabatic process means there is no heat exchange with the environment. Now the second important thing here is this part. There is no force acting on this membrane from the top, and when you remove the membrane there is no external force. No external force. Therefore, when you try to calculate the work done on the gas, it should be 0 because there is no force. When a system is expanding without any force being applied on it, We call that a free expansion. So this makes the process a free process. All right. So the heat added to the system is 0. The work done on the system is 0. That means there is no energy exchange mechanism. No mechanical energy can be added to the system by doing work on the system. No heat can be added to the system because it's thermally insulated walls. That means the change in the internal energy of the system must be equal to 0. There is nothing that changes the internal energy of the system. And in this process, because the internal energy of the system is not changing, I'm not adding heat to the system, I'm not doing work on the system. As we will find out, this will imply that the temperature of the gas doesn't change because the internal energy change is 0. And that will imply, by using ideal gas law, pressure times volume will be a constant, so you will have P initial V initial must be equal to P final V final. Why is that? Because the temperature is not changing and the number of moles of gas I have inside the cylinder is not changing. I'm not removing gas or adding any gas to this system. So as a summary, I find that this is going to be called an adiabatic free expansion of an ideal gas, and that implies the following things. Because it's adiabatic, Q is equal to 0. Because it's free, work done on it is 0. That means I have no energy exchange mechanism. The internal energy change is 0. There is no temperature change as well. Pressure times volume is a constant for this process.